Okay, I'm going to change up the format just a little bit. I think that the current format is getting a little bit laborious with all these 10, 20, 40-minute videos. And so I don't think you guys care about every little detail of all that sort of stuff. And so I'm going to start just kind of doing recaps of where I am in the process and just kind of talk about why. And this way, I think I can talk a little bit more about the methodology behind the design and not so much about the nitty gritty because we do so much of the nitty gritty that I think I end up glossing over some of the broader questions, and those broader questions are probably what's more interesting for you, my audience, kind of listening to this. So, that being said, let's go ahead and talk a little bit about this. I went to GrabCAD. I grabbed some NEMA 23 motors. No big deal there. Uh, I looked on the, I did a measurement and kind of found my spacing, and I created a feature. So those motors mount right up. Now, a lot of these, a lot of them will sell a floating bearing and a floating bearing and uh, and then a fixed bearing. I think on this design, I am only going to go for the fixed bearing, and that being what I mean by that is I'm probably not using the right nomenclature, but this type of bearing right here, which is an FK12, and you'll notice that it has a nut right here, and inside there's actually a thread on this screw, and I don't know if I touched that, the ARM 1605. Yeah, it looks like it's. I was hoping it'd highlight it for me, but there's actually a thread in there, uh, and so you can tighten it up. And this, what it does is it restricts the axial motion of the back and forth. So let's say, for example, that these motors start spinning and start to push uh, the gantry, and that gantry's cutting. It's going to create an opposite reaction. So the screw is going to want to move towards the motor, right? It's going to have a force on it. This block right here is what absorbs that force. On the other hand, a lot of systems, what they use is they'll have just an axial bearing to keep it from going like this. Now, our stepper motor is going to act as that bearing. So no, there's no axial thrust on the. And I'm getting my terminology mixed up, so hopefully you know what I mean. I tend to get stuff backwards, but the axial force, meaning the force that's moving along this way or the opposite direction, is not being absorbed by the stepper motor. It is being absorbed right here. Now, there's a radial bearing right here that basically just holds the lead screw in place. We're going to go ahead, and this is a short enough distance, I'm not really worried about that. So we're going to go ahead and we'll put a coupler right here. I might need to do one of two things. I might need to put a recess in here for the stepper motor and move the stepper motor in farther. That way I have more room, or I might just make that hole bigger, big enough to accommodate that coupler. I'm not sure what I'll do just yet. But with a, oh, sorry, we got all kinds of notifications coming up here. Okay, so yeah, so what'll happen is we'll work that out, but that's just a small potatoes, so we're going to keep on trucking on here. Um, but okay, so a couple things. First off, dual stepper motors. I said I was going to talk about this. I may have talked about it a little bit already. I am a firm believer in dual stepper motors, and here is why. Yes, I could put a beam in here, put one stepper in the middle, and one ball screw. You're saving you have a bearing that you save the cost on. You have a ball screw. You have a ball screw holder right here, and you have a motor that you get rid of. Not to mention your drive control and all that. However, I have looked at these systems, and some of them perform adequately, but I really like having a constraint on my forces on both sides. So this is a design consideration that I am not going to bend on. I am going to stay with at least two screws. Now, however, there's nothing to say that you cannot have one motor and a belt. And my original Silva actually did this, and it worked pretty well. Once I switched to two-steppers, though, I noticed a great increase. And so now about the single, if we had a single screw in the center, the problem is racking. So let's say, for example, that you have a force right here in the center, and you're cutting something right in the center. As that pushes through, you're not going to have too much of a problem because you're putting a force right here, a force on that end, and those forces combine on this end. However, the problem is once you get to the side, you have a force right here. You're having a greater force on this side than you are on this side. You are then relying on the machine's rigidity to make sure that there's no slop. Now I could tell you right now that if without a ball screw on here and without a ball screw over there, if this was just floating on the bearings, you would be able to tweak this back and forth. I will tell you this, on my large machine, the gantry alone probably weighs close to 800 pounds, probably somewhere in there. It has THK linears on it, big old bearing blocks that probably weigh 30, 40 pounds each. Not the bearing blocks, but the shoes that the bearing blocks mount to. Uh, you can move it back and forth by hand. It's just you're relying on such tight tolerances right here and right here, and the amount of flex is just. I've never seen a system that adequately dealt with it. So that is my reasoning for insisting on two lead screws. And you'll notice that these lead screws are pushed way out to the end to where you get the most mechanical advantage on your force. All right, moving on. Let's see here. Right now I am playing with a design where I have a SBR20 on top and on front. I do not know if this is going to stay or not, and my reasoning is this. Um, by the time you add your bearing blocks and then a Z-plate, the Z-plate is going to be right about here. Then you have two more of these, and we're looking probably right about here to where the router mounts. And then the router ends up clear over here. Okay, so we're saving quite a bit of space, and we can put that Z-plate right there if we mount it on the bottom. Now, there are, admittedly, there are advantages to both, but I think that in this case, I think that mounting it on the bottom, it will be a much better option. So I'll probably play with that. I had one design where I had it mounted on both, and it actually worked out okay. But in this case, I think I'm just going to mount it on the bottom, and I think we're going to be the happier for it. So, but it's all part of the process. It's why we do it this way because we learn things from it. So, all right. My next steps are going to be, I think, anyways. I might get distracted. Well, we got that's all worked out. Yeah, I think I'm probably going to move that guy down there, and then we're going to go ahead and start making the Z plate and coming up with that design. Now, there's a couple things. This changes the way I'm going to design it, so I might increase the amount of red pieces I have. That's okay. I don't know. I just don't know. I'm going to play with it and see what I can come up with. The carriage is something that I like to be very careful with. I like to be as efficient as possible with because let's face it, I want to save space and make it as compact as possible, and so. Okay, a couple things about the width right here. So we have a certain amount of distance from here to here. And oops, I got three things separate. Okay, there we go. So that's 80, almost 80 millimeters right there. If I add those 80, that's 160 millimeters. And okay, just a second. I got to pull out my phone to do some math here. 160 millimeters divided by 25.4, 6.3 inches. Okay, I like about a 6-inch a 6-inch wide carriage is about ideal for me. So that means that remember that your that your cutting area, that your travel area is equal to the length of your tracks, which is this right here, minus the width of your carriage. So this is actually going to work out perfect. That means that if the carriage is all the way at the end, my bit is going to be right here. And all the way at the other end is going to be right here. Perfect. That means that we're going to be able to maximize our travel area. I'm actually very excited about that. And I love how compact it is, that this machine overall will only be 6 inches wider. Well, by about 7 inches probably. Not including the stepper, of course, because we're going to have a stepper sitting out here. Then the actual footprint of the machine. And that's one thing that, I cannot stand is having a machine that is so much bigger than your cutting area. I want something that can fit in people's workshops and not take a whole lot of space. And so I am super thrilled about how this thing is coming out dimension wise. Now, okay, right now it's as ugly as sin. Um, I like the lines of a sports car or a beautiful woman or a streamlined CNC. I think those are all beautiful things. And we're going to add a little bit of flair to this as time goes on as well. Um, my general rule for flare is if you could add it without adding significant machining operations or having any mechanical drawbacks, then I will do it. So, uh, anyways, it's other people may disagree with me, and may put form over function, or function over form every time. But for me, I just, I really like to consider my the stuff I engineer kind of works of art, and so that's the one way I'm going to think about it. Anyways, okay, awesome. So stay tuned. This thing will look different next time you see it. Thanks for hanging around, and you could probably expect the pacing to pick up a little bit from here, and we're going to have less muddling around in SolidWorks and more design uh, talk coming along, which is probably why you're here. So, anyways, thank you so much, and have a great whatever time of day it is. And I guess we will talk a little bit.